Right, so 2 years without getting on stage, I'm a bit anxious, and I thought, okay, just do better than the previous guy, throw in a few jokes every now and then, and that was way before I saw the program. So now I only have a few jokes, and they're not really good at all, so sorry about that. Let's get started. That's me. I should say that's us. I'm really just the face behind the team for obvious reasons. I work at Pyrum, and you've heard of it. We are looking for hiring people. If you are inquisitive, you like to think about challenging problems, and you are curious about, financial challenges, then come and speak to us. This is a great place to learn and grow. Let's get started. So I want to prime your mind on a complex problem. Not complex in the sense that it is difficult to write a solution, in the sense that it is really hard to come up with an efficient solution. So this is just going to be a token example for me. The point is not the problem itself, it's more the class of problems. And we can go back from there a bit later. There exists actually a lot of techniques to try to come up with more efficient solutions than the obvious ones. These techniques usually rely on a set of assumptions that you are making about your inputs. And they do work well if you stay within the boundaries of those assumptions, but as soon as you drift away from them, then usually the solution collapses and becomes extremely, extremely slow. So here is a very simple, very clear solution that uses a few of those techniques that I stole from that great book here. It takes a couple of lines of Scala. It is extremely efficient if you just abide by two simple conditions. But as soon as your inputs do not respect those assumptions, then suddenly you go from a solution that is linear to something that becomes exponential. Here is my rewrite. Right, so let me go back. Not much has changed. I'm just switching a few types there. There's this M list that replaces the traditional list that we'll talk about a bit later. And then there is this mod type that makes its appearance. Otherwise, it's the same size, right? And I'm going to make the claim that this solution is just as slow as the other one on the first invocation. On the other invocations, the following ones, it's going to be nearly optimal, assuming you respect some set of conditions. So, what I want to focus on is, instead of talking about how to write your programs using the library that I'm working on, is more about what's happening under the hood, what is the technique that I'm using. I find that way more enlightening than talking about map and flat map or stuff like that. You've done that 1,000 times, and I'm boring myself to sleep just thinking about it. So let's talk about incremental algorithm, which is the techniques that I've been working on in recent days. So this is a fairly newish technique in computer science terms. There's a growing body of research around it, and I've been focusing on one particular area. But generally speaking, the gist of it is that it works on three things. The first is you're going to make the assumption that your program is going to run many times, right? So that's something that supposedly we can agree is very frequent. But the second assumption is that your input from one execution to another is not going to change drastically. Now, that is perhaps something that happens less often. But if you take two invocations, two consecutive executions, the diff between the inputs has to be a small percentage of the input itself. And if you abide by these two assumptions, then the idea of incremental algorithm is that you're going to perform the minimum amount of work that is needed to move the previous solution to the previous invocation to the solution of the current invocation. Just by shifting a few things, you arrive at the new solution. And obviously, you can write algorithms that are specialized, but that's not what I'm talking about. I'm talking about a general framework for thinking about these incremental algorithms, and I want a technique that works for everything, not just the knapsack problem. In fact, if you want to take the sum of a list of integers, that's exactly the same technique that applies. And the method that I've been focusing on in particular is called self-adjusting computation, and it works in 3 steps. First one is you want to identify the things that you want to make incremental. And this is where usually you will use your creative license and your understanding of the problem domain in order to define what is going to change from one invocation to another. So this is where most of the difficulty is, if there is any difficulty. The second step is on the first invocation, what you're going to do is you're going to reify like the execution itself into a data structure that represents the flow of your algorithm. And in doing so, you're going to mark all the memory locations that have been read and have been written to. And this essentially is going to form a graph of relationships between components of your program. Once you have that data structure, when you have the next invocation, what you're going to do is to effectively identify the changes by tracking the locations that have been updated and propagating those changes through your data structure, re-executing only the parts that have been affected by these changes. And you have to do it in order, obviously, otherwise all hell breaks loose. So let's take it step by step. The first thing is you need to identify those modifiable, what I call modifiable variables. And these are the 2 data types that I introduced earlier. So mod is like the general set of programs that you want to make modifiable, adjustable, incremental. It's a type constructor like option, future, UIO, nothing groundbreaking there. mref, though, is the data type you use to identify those locations that you want to make modifiable. All right, so this is usually the crux of how your program is going to behave. Once you start rewriting using modifiable references, it's going to have a huge impact on like the propagation algorithm, and essentially that's going to be the only performance cost. And just to give a small example of what kind of choices you can make, I have these two data types that represent a cons list, just like your normal cons list. But here, in the first one, I'm making the choice of setting the tail as a modifiable variable, and in the second one, setting the head of the list as the modifiable. And the result is very different in both situations. In the first one, you can write algorithms that will react to a list that can change in size. So assuming, for example, that you want to sum a list of integers, and you write your algorithm, usually a recursive algorithm, and somehow you pass a list that has the same elements except for the last one, it has an additional element. With traditional methods like dynamic programming or whatnot, you're going to have to go through the whole list over again. Here I'm talking about something that can only take that last element and add that to the existing sum, reducing the algorithm to a constant operation, effectively. Second case is where the head of the list is modifiable, and this is where usually the list stays pretty much the same, but the elements inside that list will change. Right? So again, the execution here is going to be very different in both situations. So you have to be careful about that when you design your algorithm using that method. that's it. Once you are done, then let's keep that. Then the second step is under the hood. You have a runtime that is going to take your mod program, and on the first invocation is going to build that data structure, tracking effectively every function call and every read to your memory location. So this data structure is essentially a graph where the edges, where the vertices are the memory locations, and the edges are the read operations inside your functions that accesses those memory locations. Once you have that, then you need to be careful to track the sequence, the ordering of your program, of how it unfolds. Why? Because on successive execution, you want to make sure that you re-execute the right thing in the right order in order to reach the correct result. If you don't do that, then you won't, it's unlikely you will get a correct answer. Now, what happens if you make a change? Let's say that, and I have great taste, by the way. I decide to sell my CD collection, buy a few clothes. Now suddenly, that part of the graph that is accessing that element, that memory location, becomes invalid. I need to just get rid of it. I need to re-execute the corresponding part of that program. And that means that there is a kind of a recursive behavior there. You're going to re-execute that program with the new value, and depending on the logic inside that function, you can have branching, you can have calls to other functions, etc., etc. The subgraph behind that node I here needs to go away. It has to be rebuilt from scratch. And this will have perhaps an avalanche effect depending on the algorithm. It can have impacts on other parts of the graph. So this is a very recursive process. So first thing is you delete the subgraph, you re-execute it, and what you get back is another graph. And obviously you need to keep track of that. You need to relabel these edges so that the ordering is still valid in the whole graph. So this is something I don't really cover in this talk, but it's a problem known as the order maintenance problem in computer science. Fascinating. There are many very elegant algorithms to solve that. Anyway, once you have propagated those changes, you're done. You have your answer, and the good thing is that, depending on your algorithm, there's a huge part of the graph that you haven't really touched. So there's a huge collection of results that you were able to reuse. So if you read between the lines, there is really a trade-off between using space and time here. And in particular, we are going to memorize. It's not really memorization, but we're going to keep in memory previous results so that we can reuse them and when they are necessary. And there is an eviction mechanism that is natural when you re-execute the graph because you just delete whatever is not necessary anymore. So this is the idea of the technique, and I have a work-in-progress library that I'm working on, and currently it's very imperative. I don't really want to bother with purity or functional stuff, just because to me that's a layer above an imperative solution, usually. And my implementation is very faithful to the original paper. It works using mostly continuation passing style. As you can see here, there's this mod function that is effectively the entry point for writing modifiable programs. And it gives you access to that dest data type, which is just a way of having some kind of type safety in that a dest data type is the destination of your program. So that's where you are going to write your final solution. And in fact, write is the only method that allows you to manipulate that rest data type. Inside that mod function, the second parameter is where you have all the reads. And all the reads, effectively, what they are going to do is access those memory locations. So this read is a very direct implementation in that all it does is it adds an edge to the graph data structure under the hood. It's very easy to implement. And finally, the programs that are made incremental, they are identified by this data type called changeable, which is an abstraction just to make sure that, again, you have some type safety. Anything that happens within that mod method is a changeable program. You cannot launch the missiles or anything. It's all pure. Once you have that, then there is these two methods which are really imperative looking, and they result in the unit data type. The first is change, and change is how you effectively you have this set of modifiable references, and you want to change them, and then you want to see the impact of that change. So change is the method you use to do that, and in itself, all it does is it tracks the changes that you introduce in your next invocation. The next step you need to do is to propagate those changes through the algorithm. That's the propagate method, and that is effectively going to reflect to do that propagation step that I mentioned earlier. This is the state it is in at the moment. It does work. It's not stack safe though, so I still have to work a bit on that runtime system. There's a few things that I need to care about, but it does work really well. I can see massive improvements on the examples, at least, that are listed in the paper. Have similar results. I cannot yet write, let's say, concrete business use cases just because of the stack safety issue, but hopefully I will be there soon. Now the question is, how do I yeah, so just as an example, using that formulation, suddenly the rendition of this knapsack problem becomes a bit more convoluted. You have to use continuation passing style. It is hard to follow. I do not want people to write using that style at all. What I want to go back to is something a bit simpler, like Zio. So there is a very obvious way I could do it. I could do that. I could just I could just generate, I/O out of all of these methods, because effectively what they are going to do is create data structures under the hood, do mutation and all that jazz. So it makes sense to think about them as effects, even though this library is mostly interested in CPU-bound in-memory computations. There is no access to the external world at all. So UIO is interesting. It's a bit too large, in my opinion. I think I'm going to try and come up with something else. And in fact, the more I think about it, the more I realize that modifiable programs and modifiable references look a lot like the ST monad in Haskell. I don't know if you're aware, but effectively this data type allows you to do stateful transformation in your code by having these stateful variables and this stateful data type that you can use to effectively write imperative code that has the same kind of performance of imperative implementations, although with a functional style. So it does look very similar. There's a few differences that I would like to highlight in my solution, but this is the direction I'm going to. Perhaps I will open that up for external opinion at some point. That is my hope, at least. So as I said, I didn't create anything. I just translated what's already out there. There's actually this idea of self-adjusting computation is a huge footprint in the ML language. There's an implementation that is very famous, has been written by Jane Street, and they have a very interesting talk on that implementation. My understanding, though, is that it does go very far from the original idea. It has I think the first implementation was just like very far from the original concept, and then they made, they tried a few different versions where they tried to come up closer to the original paper, just because if you read that paper, there's all the information you need to create something that is extremely efficient. All the proofs are written, all the efficiency, the space-time complexity has been studied. If you just follow the script, then the only implementation you can come up with is a correct one and an efficient one, save for the stack safety. That's it. Thank you very much for listening.
There were questions from the internet.
Oh.
From our friends outside. One of which is, what font were you using? That's the big question.
Wow. So in a previous life, I did study typography for a while, and I can give references there, definitely. I do find some pleasure in choosing the right, or what I feel is the right combination of fonts.
The lovely monospace font. Yeah.
Thank you. Yeah.
Hi. Well, I already asked this question, but for the internet, I asked what font, and that you probably were able to figure that out. But we don't know the answer yet, but you're going to get back to
Which
us.
one, the monospace?
The monospace. What's the monospace?
Monospace is called Operator.
Operator.
Yes, go to typography.com. That is one of the best type foundries in the world. They do amazing stuff, and yeah, Operator is, as far as I know, the only monospace font that has a, style.
It was lovely. That's my only question from the internet, I think.
Cool.
But if there are other questions here, meanwhile, I'll ask, what's your concrete use case? What drove you into this? What sort of trouble were you was it really for did you have an AppStack problem personally?
Yeah, great question. So initially, I've been thinking about that for a long time. I used to work in my previous job on websites, and I'm one of the 3 people who doesn't like React at all. I really hate it. And this seemed like a formulation, or at least conceptually, a good solution to writing something that only reacts to and that only performs the minimum amount of work for UI work, right? And that's what the incremental library does mostly. But the problem is that there is a cost in memory. And if you're not careful, even a huge cost in memory. Even if it's a constant factor, that constant factor is very large. And so I don't think that's what I would use now. I would probably go to something called incremental lambda calculus, and I would even use some of the method used in Quill to do stage compilation. Anyway, yeah, financial inputs that we receive at work. We have some problems that involve very expensive compute-bound computations, and the data falls into that set of assumptions. It's a lot of data, but between 2 invocations, there is not like a huge difference between the inputs. And so this is where I have as much memory as I need. I can store that intermediary state whenever I want. And so that's why made me think about that again.
Awesome. Thank you. Thank you so much.
Thank you very much.
All right.
change the variable back to the original value, that it can find the
So in the paper, you have like the basic framework, which is the thing that I wrote, and there's also a lot of purely functional languages that are defined in that paper that evolve the basic framework, that give more features, so to speak. And one of them is selective memorization, where you can effectively decide what you're going to keep in memory. I mean, the framework itself does a good job already, but there is sometimes too much stuff that is kept in memory by the basic framework, and that leads to a lot of waste. So selective memorization is one solution to that. It's not a paragon of correctness, though, as far as my understanding is concerned, and that's the extent of my knowledge. I know there have been a lot of follow-up papers, especially in the big data space, where they try to find the right spot between, you know, that trade-off between space and time. I don't know if that answers your question. I need to do more research, probably.